I will now briefly introduce our first keynote speaker, Yoshua Bengio, who is probably well known to everyone in the room and is distinguished now for other reasons, as being one of the few sort of lions of the deep learning field who has not yet been absorbed by a major corporation and is still free to tell us what he thinks and what he's working on. So we got to pick his brain out before he gets gobbled up by Northrop Grumman or whoever is next. I don't know. I'm just joking. But yeah, we've seen that deep learning has been very successful in its applications in recent years, and because of that, it's no surprise that industry as well as academia has become increasingly interested. And Yoshua's work on deep learning in many aspects, both theoretical and practical applications in computer vision and many other areas, has been, it's not my field, but it's been very, very interesting to me to follow, and I've very much appreciated not only the quality of the work, but the openness of the work with so much source code online, stuff that you can really dig into it and understand. So I think he can introduce himself further better than I could, so I'll turn the stage over to Yoshua Bengio.
I think we should turn the light off.
Yeah.
Yeah, I think the projector's on. It's just, I think it's right there.
Oh, this one?
I don't know.
We set the light on.
Anyone understand the lights in this room? Oh, there we go. What did you do? It was me. Yeah. There we go.
There you go.
Right.
Perfect.
Damn it, can't see the film. It's in black dark.
All right. Is it working? Are you hearing me? Yes. All right. Thank you very much for the invitation to give this keynote speech. I'd like to say that I have a lot of sympathy for a lot of the things you've said and feelings you've expressed about being one of the few people in the world interested in AI 1 or 2 decades ago. In the early 2000s, it was very, very difficult in my community, which is the LIPS community in ICML, to think about, express ideas about machine learning going beyond simple industrial applications and really aiming at AI. But things have changed, as you said. So I'm going to tell you today about some of my views and some of the things that have been going on that I won't have really time to do a lot of technical detail. Try to stay at the level of ideas and concepts. And I would really welcome your interventions and questions and comments anytime during the presentation. So feel free. I'm trying to, there's not a lot of light, so I hope I won't miss your raised hands, but please interrupt me anytime you feel like. Right, so I want to understand the principles that give rise to intelligence, and my focus is on the learning aspect because I believe this is a necessary condition for building intelligence. So I'm interested in understanding the mathematical and computational principles that allow one to learn from examples to acquire knowledge. And I'll tell you about deep learning, which has known kind of breakthrough in the last few years. Basically, it's about machine learning algorithms inspired by brains, and most importantly, based on learning multiple levels of representation and abstraction. So I'll talk about this notion of representation a lot in my presentation, and I hope it will become clear. As Ben said, it had a lot of impact in the last few years. It has essentially revolutionized the fields of speech recognition and object recognition. But its impact is widening.
People like to see here.
So in speech recognition, almost all of the current state-of-the-art systems use deep learning and object recognition as the same kind of move that's happened in the last couple of years. But we see these techniques expanding into other areas of computer vision. Natural language, I think, is one area where the most growth is going to happen in the next couple of years. Things like dialogue, so we're getting close to actual interactions between humans and people. And of course, reinforcement learning, as you've heard Ben talk about with the work of DeepMind. Although I won't talk much about that, I think it's a very important component of the expansion of deep learning into all kinds of areas. So in speech recognition, one can measure the impact by looking at the progress of error rates. And I've taken these numbers from the Microsoft speech group, but there are people who think that other numbers, other data sets give other numbers, but these ones are pretty impressive. So in the 90s, actually, I did my PhD about the same time as Ben, and I was working on neural nets and probabilistic models for speech recognition. And speech recognition performance kept improving after I finished my PhD in the 90s, thanks to, well, not so much improvements due to better algorithms, although the engineering got a lot better, but mostly thanks to a lot more data and faster machines. But eventually plateaued because they were, I think that the speech recognition community was kind of stuck in a local minimum in terms of algorithms, something that is a lesson for all of us. Then deep learning was explored for speech recognition in a serious way, and in the matter of a couple of years, the error rates went down drastically. So that nowadays, if you have an Android phone, it uses speech recognition based on deep learning, and in fact, there's a recognizer that's sitting on Google's servers, but there's also one on your phone, in the case where you're not connected. That doesn't do such a great job, as much as a good job. It's a smaller network, but it's there and it's used. In speech recognition, a similar thing happened with the ImageNet dataset that has about 1,000 classes of objects. So we have one central object, like in these pictures. And you see here examples of outputs of the network trained by Krzyzewski, Sutskever, and Hinton. They compared themselves in a competition which people in computer vision considered was the serious baseline to beat in order to be taken seriously. And not only did they beat the baseline, but they moved in a drastic way down with respect to the other competitors and previous years where progress was measured by a fraction of percent improvement. They went down from 26 to 16, and now we're at about 12. So things have moved a lot. You can try it for yourself. So if you go to this website, deeplearning.cs.toronto.edu, you can paste, you can upload images, or you can paste URLs of images. So I just did that yesterday night. I went on Google image search and I grabbed some images and I pasted the URLs. And here are some of the things I got. And I really didn't try to make the thing look good. I just tried a few images and I pasted them here. So this is, it says this is a convertible. It knows only 1,000 categories, which you can think is a lot, but it's much less than the number of things that exist, of course, which is quite reasonable. And it also says sports car, 1%. On this, it says it's a chimpanzee or a chimp or a gorilla. And this is a funny one. It says it's a sports car or a race car. And this one, it has less confidence. You see the percentage here, 34%. Killer whale, killer tiger shark, whatever that means. Scuba diver. So these are pretty reasonable answers. This one is fairly easy, German Shepherd. So it not only knows about dogs, but it knows about breeds of dogs and cats. So I encourage you to just try it out for yourself. And it's not perfect, but if you had any kind of contact with computer vision, before these things came about, it was very hard to take random images from the web and get something sensible. But it's not yet total perfection, but it's amazing. It's much, much better than what was there before. It's not just the numbers, it's qualitatively better. In my group, we apply these kinds of things to emotion classification from short videos, including audio and images. And we won a competition using deep learning against other techniques. But there's been a whole lot of groups using these techniques for all kinds of things. And in 2013, that has prompted the MIT Technology Review to declare deep learning one of the breakthrough technologies of the year. And the media, as Ben said, has been talking about it in the New York Times and Wired, and talking, of course, about the deals on Facebook and Google trying to compete for DeepMind and other companies. Eventually, Google buying it for $500 million. So this is all nice. And there's a big potential for these techniques. As Ben said, I agree that this is just one approach, and I'm a very strong fervent of diversity in science, and I believe that we need to explore all kinds of things because we don't know what the right outcome is going to be. But what I'm after with deep learning is the part of AI which people call perception, and I would also call it understanding, which I think is slightly better. So we want computers that can see and hear and understand natural language, understand human behavior. And we also want to use this research to better understand how humans and animals might actually do these things. And of course, companies are interested in using this for technology, personal assistance, self-driving cars, and whatever. Okay, now let's talk about more fundamental questions. What is driving my research beyond the quest for AI, and how I think we can get there? First of all, to have an intelligent machine means a machine that can take good decisions. And in order to do that, it needs knowledge, as we all know. And the basic question of AI is, well, one of the basic questions at least is, how is the machine going to get that knowledge? So we can either feed it that knowledge, and that was the expert systems way, and it failed. And it failed because we don't have a complete explicit access to our own knowledge, so we can't give it to computers. So they have to acquire it, and that means learning. And learning means a bunch of things. One way to decompose learning is into these three things I wrote here. One is prior, so you need some priors. You can't really beat tabula rasa. And we want to have the broadest possible priors that will allow machines to learn about all kinds of things we have around us. But that's not enough. Machine learning is a combination of statistics and computer science, and the efficiency of the algorithms is really important. So there's both a notion of efficient computation and optimization and search, which play a role in all this. Now, the statistical aspect is really central, I think, and I've been focusing a lot on that. So the view that I'll try to share today about generalization, which is the statistical aspect of machine learning, is a geometrical view. I'm trying to think about generalization as answering the question, where should we put probability maps? This is just one view of generalization that I find very convenient. And, it helps me to think about the next topic here, which is the curse of dimensionality, which is what happens when you try to learn in high-dimensional spaces with many variables involved that have an exponential number of configurations, where not only computation is hard, but generalization is fundamentally hard because there's a huge number of ways in which you could generalize, and most of them are wrong. So how can you possibly cope with that? And my answer to this question is, in the last bullet, is what I call disentangling the underlying factors, disentangling the underlying causes that explain the data. And that, in an AI sense, means making sense of the data. So we want computers that can make sense of the data. So that's sort of my program. Not exactly how, but my goals. All right, so let's go back to the basics of why it's hard to deal with high-dimensional spaces. I'm sure you've all heard about the curse of dimensionality. Just to remind you, the issue is that we're trying to say some things about configurations of variables we have never seen, and in high dimensions, the number of configurations that we can possibly see in the training data is a tiny, tiny fraction of all of those that can possibly exist. So the classical statistical methods for machine learning exploit a very simple prior, which is a smoothness prior, that says, well, we can generalize by saying that the configurations that are probable are close to the configurations we've seen in the data. So if I've seen some examples in some configuration, in one of those cells, I can roughly say in the neighborhood of that cell, things should be similar. And that's good, but it's really not enough, and it leads to the curse of dimensionality in the sense that those neighborhoods either are too small to allow you to generalize far from the data, or they're kind of too large and they cover everything and they're useless. And they assume that the function you want to learn is super, super smooth. Another thing to keep in mind is when you're dealing with AI, when you start thinking in a sort of geometrical way, is that the kind of data you're looking at has a very particular structure. And it's true for vision, it's true for language, it's true for audio. What it is that the data concentrates in some, or near some lower dimensional regions, which we call manifolds, but it's an abuse of mathematical language, of course. What we mean is that most of the possible configurations, say sequences of letters, pixels in an image, most of the possible configurations are unlikely. They don't correspond to the kind of data we care about. That if you pick pixels randomly, you get these kinds of white noise images, and the set of images that correspond to natural images is occupying a tiny, tiny volume in that huge space. And but these points are not isolated; they are connected to each other. The probable values are close to each other, so that's where the notion of manifolds comes in. For example, if you take an image of 4 and you rotate it, translate it, and so on, you create a set of probable configurations of pixels, and we call these manifolds. And it's very interesting to think about the machine learning problem in those terms. So that leads to the sort of this geometrical view where the notion of generalization is about guessing where probability maps should be put. So we know that the examples we have are probable. So if we have an x, y example, we know that that configuration of x and y is likely. And for a new x, maybe we would like to know what other values of y are likely. Right? That's the supervised learning problem. But in unsupervised learning, it's basically the same question, except there's no special role for X and Y. So we have this challenge of recursive dimensionality, and the way I'm going to try to solve this problem is by this notion of representation learning, where we're going to take the data from the space it is in and try to map it to a new space, a new representation, where things become easy. Because if the manifolds that you're thinking about were flat and concentrated in a few dimensions, then the problem would be easy. So that's what we're going to be doing. We're trying to transform the data in new spaces, a kind of new set of features or new random variables that, that make the statistical modeling much easier and make it easy to do inference, to answer questions, and so on. All right, so I guess I've said all these things already. So representation learning can be viewed in more practical terms as replacing the handcrafting of features, that is the common way that machine learning is applied, and usually takes something like 90% of the effort when you deploy machine learning systems, by instead of human-designed features like machine learning itself to decide how the data should be represented. So that raises the question, what is a good representation? And the kind of answers that I and others have been sort of dreaming about is that the right representations are the right features that explain the variations in the data, the right factors, the causes of the data. At least that's one way of thinking. And you can take these ideas of learning representations and do pretty powerful things. For example, at Google, they've used this to build their Google image search engine. And what it does is it learns representations jointly for images and for text. So text keywords, the kinds of things queries that you type on the search engine. So actually this is work by my brother, Yoshua Bengio, and collaborators. And what they learn are two functions. A function that maps an image to some vector space, like initially I think they had 100 dimensions, I think now they probably have more like 1,000. And there's another function that maps keywords, queries, into the same space. And those two functions are learned jointly, so that when somebody types a query, then clicks on an image, the representation of the query and the representation of the image land near each other. So that's a pretty simple principle, and it works really well. Actually, this follows up on earlier work that I started in 2000 with a NIPS paper on learning representations of words. So the idea was that it was a big departure from the way that statistical language modeling was made, and where we, instead of representing words as symbols and their relationships by co-occurrence counts, we said that one really important intermediate thing to do with words is to learn a set of attributes for them, which we call embeddings, because we think again in terms of manifold learning. So we map words to a representation. Here you can't see the words, but actually they are organized in, if you do a 2D dimensional reduction to visualize, they're organized in groups corresponding to parts of speech, like verbs and nouns and things like that. And if you zoom in, you start seeing that words that have similar meaning get learned to be close to each other, like countries and things having to do with parliaments and elections, and verbs together, and conjugations of the verb to be together or to have together. But something really amazing happened last year with these kinds of embeddings. Maybe by playing with these, Tomasz Mikolov found that these vectors that we learn for words in a purely unsupervised way actually display some kind of analogical relationships. So if you take the representation for king, which is a vector now, and you subtract the representation for queen, you get a vector which is roughly aligned with the difference between the representation for man and the representation for woman. So what that means is, if somebody asks you, king is to queen what man is to what? Well, you can answer by just adding and subtracting these things, and you find woman. And you can answer the same thing about, the relationship between Paris and France is the same as Italy and what? And the answer would be Rome. And one way to understand what's going on here is that it's like if, imagine in the representation we're learning, you have a dimension or a bit that indicated male versus female, right? So king and queen would have essentially all the other bits the same. When you subtract these two vectors, you would get just that bit. And the same for man and woman. So that's why you're seeing this.
Can you represent relationships of some sort in this vector space, or is it just similarities?
You can represent relationships. So I had a paper about 2 years ago on how you could learn to represent relationships between objects, and you can think of, in a more general sense, as relationships as verbs. So we trained this on knowledge databases like Freebase and WordNet, and using free text from Wikipedia, where we took sentences, subject, verb, object, and we learned presentation for the subject, the verb, and the object, so that it basically learns the joint distribution of the three things. But as an intermediate step, every word or every phrase is mapped to one of these vectors. And you can visualize these vectors in a similar way. And then you can use these things for question answering. So if you give me the subject and the verb, I can tell you which object is, fits best according to the model. So these kinds of representations are very powerful. And there's a lot of work right now in NLP moving forward in this direction. Yeah.
Have there been any expansions to the neural word embeddings, like the visualization with images or sound? Or
Absolutely. So, I mentioned this older work at Google Image Search, but there's a lot of more recent work that's very exciting. For example, Richard Socher has worked on how you could use these to generalize, to classify objects that you have, for which you have never seen an example putting together the word and the image. Simply because on one hand you have semantic relationships in text and visual relationships from images, and you learn these representations, and you can get these amazing generalizations that allows you to generalize from zero or very few examples, thanks to the fact that you're learning jointly a representation for words or text and a representation for images. So you can map one to the other and predict one given the other. I mean, the really crucial thing here is that words in the symbolic traditional way don't come equipped with a metric. They don't come equipped with a similarity notion. So I can, but once they have, I can invent a new word that has a meaning even before I put a name on it, right? If I have an image for something, and I map it to that common space, then I know what other words are nearby in that space, and it has a meaning, and it's not just a symbol. So we've been, in last year, we've been using these kinds of things for machine translation, and there's been a kind of breakthrough, and I think it's just the beginning of using these techniques for machine translation. So we got a nice improvement in the English-French translation using these kinds of systems, using recurrent nets that combine depth and recurrence. And at the last ACL, just a bit more than a month ago, a group at BBM has been using these kinds of models for machine translation, and they won the Best Paper Award, and they were able to get the Arabic-English translation to improve by 6 blue points, more than 6 blue points, which is, if you know anything about machine translation, it's a huge jump. So I think there's going to be more of that coming the kind of approach that we've used for these systems is inspired by a lot of work with the idea of autoencoders. So we think of machine translation as an encoding and decoding problem, where we start from a sentence, say, in English, and we're going to map it through an encoder to a fixed size representation. So we need something that can deal with variable size input, like a recurrent net, and maps to a fixed size representation. And then the decoder is another machine that takes backwards a fixed size representation and outputs a sequence. And the way we do it is the decoder is probabilistic in the sense that you can sample and source, and in translation makes a lot of sense. We know that a given source sentence can be translated in many different ways. So what we really want is a distribution over the possible translations. And the nice thing with this is that you can train it with, of course, French, English pairs, but if you plug the encoder of English with the decoder of English, you can use unilingual data, which is in much greater numbers, to train the encoder and decoder. And if you have other languages, we're working with European Parliament data that has 25 languages, then you can have one encoder-decoder pair for each language, and you can learn the kind of universal language intermediate representation. We haven't done that, but this is what we want to do, where the number of parameters that you need for this doesn't grow quadratically with the number of languages, but just linearly, which makes a lot more sense. All right, let's go back to basics and why we want to not only learn representations, but learn multiple levels of representation, which is the topic of deep learning. So there's, on one hand, a lot of theoretical results suggesting that representing functions through deep computation, or deep circuits, as it's called in that area, can give you an exponential gain in representation, meaning that some functions can be represented a lot more efficiently with a lot fewer computations if you allow your circuit to be deeper. I think I'll have a slide later about this in a bit more detail. Of course, there's a lot of inspiration from the brain, as I mentioned. The brain has a deep architecture, and this is particularly clear if you look at the visual cortex, where we understand that it has a series of representations, of transformations of the raw sensory data into gradually more abstract features. There's something also about the brain that kind of, I think, answers in part one question that Ben had. And there's a lot of evidence that cortex, at least, appears to have kind of generic learning algorithm. Although when you're born, different parts of your brain are specialized to different functions. Depending on what you do in life, the same initial neuron may end up doing very different things. So if you have a stroke and one part of your brain which is supposed to do function A is destroyed, then the nearby neurons, which were initially supposed to do something else, will take on the job. If you're born blind, then your visual cortex will start looking at the sounds and doing something with it. So there's a lot of evidence like this that there is a general purpose recipe in the brain. Of course, it's not a proof, but I think it's a very strong incentive for the kind of research we do and you do. Also, I think it's just much more exciting to look for that kind of general purpose recipe than trying to solve each little task separately. So I don't need to convince you of that. Another motivation for deep learning comes from sort of thinking about cognition and how humans solve problems, where we, for example, we compose solutions to build systems. We first learn simpler concepts and then we compose them to represent more complicated concepts and so on. One kind of decomposition that's fairly easy to understand is the part-space decomposition, but by far this is not the only thing that happens in deep nets. So this illustrates what happens on images of faces. This was done by Li and Ring at Stanford a few years ago. And they had a network that was trained on images of faces, in the lower level units, what we see is what each unit, well, some selected set of units likes the most. So the kind of thing they respond to. And in the lower levels, they basically are edge detectors. Higher up, they detect parts of the face, and higher up, they detect particular kinds of faces. So this makes a lot of sense. But in general, you know, how do we write programs? Do we write programs as, you know, one main program with lots of pieces of code that's cut and paste? Well, some students do that, but it doesn't work really well. What we want to have is programs like this, where pieces of code are reused over and over again in a deep hierarchy. So this idea of a deep hierarchy can be justified on theoretical grounds in many ways. And one very simple intuition comes from thinking about polynomials. So imagine you have a bunch of numbers here. You're going to build polynomials by doing additions and multiplication in a circuit where each node does multiplications and additions. Then what happens is that and you allow these nodes to compute things that can be reused higher up. So the computation, for example, of x2, x3 here can be reused in 2 different ways higher up. And if you go even higher up, it's used in 4 different ways. So if I were to flatten the computation by the top level node into one sum of products, it would redo the x2 times x3 many times. So it's not just going to be saving computation, you're also going to be saving in terms of learning, because if you think of each of these nodes as something in be learning, there's both a computational advantage and a statistical advantage. And you can see that it's exponential in the depth, right? How many times is this term going to happen further downstream? It's going to happen exponential in the depth, right? 2 to the depth here. So that's kind of the intuition behind many of the results that exist in the literature about the expressive power of deep architectures. One thing to remember, in the 90s, people thought that, well, maybe it wasn't worth it to train deep neural nets because we knew that 2 layers were enough in the theory. But those theories that say a single hidden layer is sufficient, it gives you universal approximator. They don't say how many units you need, and actually you need in general you need an exponentially large number. And of course, if I take a random function, I can't do better than that. But if the function we're trying to learn has some structure, there's some prior that that makes sense here, then maybe we can represent it much more compactly, even though it corresponds to a very, very big, shallow network. The last piece of work we did in this area was presented at the last IPR conference this year. And it regards the kind of networks that are currently used in the state-of-the-art systems for object recognition based on so-called rectifier and max-out units. And we showed that the number of regions that such deeper networks can represent is exponentially larger than shallow ones. I'll come back to this question of number of regions later, and it will maybe become clearer. But one sort of cute thing is that the thinking we had in the theory proof there is based on thinking of what each layer does as a kind of folding. And the more you fold a piece of paper, the more different intersections of regions on top of different regions you can get. So I'll leave it there for now. So in 2006, there was a kind of breakthrough in the sense that previously we didn't know how to train deep nets practically, although many of us had the intuition it was a good thing to do. That really started with Jeff Hinton, and Yann Lequin and I worked on this at the same time. And basically what we did is we were able to train deep supervised networks by first solving a harder problem in principle, which is unsupervised learning, but doing it in a greedy way, layer by layer, learning a new representation on top of a previous representation. And Jeff did it with RVMs, and I did it with autoencoders, and Jan did it with sparse coding. 1 year later, I wrote this paper called Scaling Learning Algorithms Towards AI, which was a kind of manifesto of what we thought in those days, why it was important to go away from the mainstream machine learning based on SVMs and things like that. both for theoretical reasons and because we thought that in order to really move towards AI, we needed to have systems that scale in terms of the amount of human labor you need, but also in statistical sense and in computational sense. All right, so it started with unsupervised learning, and then in the last few years, the rage has been with supervised neural nets. Although initially we needed these unsupervised learning to really train deep nets, in recent years we found a bunch of techniques that allow us to train purely supervised deep nets, backprop nets, without even unsupervised pre-training, which is the trick I mentioned earlier. Thanks to things like better initialization, different kinds of nonlinearities, and in some cases using some changes to the basic stochastic gradient descent method. But unsupervised pre-training remains a very useful thing to have when you're dealing with rare classes, when you're trying to do transfer learning, when you have small label set, or maybe small label set for some classes and so on. In general, as a regularizer. So in 2011, we actually won two competitions, two transfer learning competitions, where the objective was to learn representations on some classes and then use those representations on new classes and be able to generalize for these new classes from very few examples. And those curves show accuracy on the y-axis against the log of the number of labeled examples for the new classes. So these are learning curves. We'd like these things to rise up as quickly as possible. So we want to have as few labeled examples needed in order to get a good performance. And what you see in the pictures is what happens when you do this on raw data or after putting your classifier on top of the first layer, the second layer, the third layer, the fourth layer for one of the data sets where the impact of depth is really striking. Okay, so I believe that in order to go and bypass the curse of dimensionality, you need to introduce some extra assumptions. But they can be very broad, they can be very large, broad priors. And one of them is the notion of abstraction, which basically comes from compositionality and has nice mathematical justifications that if the kinds of functions you want to learn can be expressed as a composition of simpler things, then you could have an exponentially important advantage compared to not taking advantage of this prior. To see this in a very simple, concrete case, I'm going to highlight the difference between non-distributed representations and distributed representations. So first, let's talk about how a lot of machine learning is done, has been done for decades. The prototypical example would be clustering or nearest neighbors, but that includes RBF SVMs, decision trees, non-parametric classical, non-parametric density estimation with local kernels. So what all of these methods do is take the input space and break it up into regions. And they're very powerful in the sense that they can break the space into as many regions as you need, so long as you have enough examples to tell you where those regions are and what the output should be for each of these regions. So in nearest neighbor, you need exactly one example per region. In clustering, maybe you need a bit more. But the important statistical question here that I want to ask is, how many regions can you get for how many parameters, or for how many examples? Right? So here the relationship is linear. You need, order of n examples to tell you about order of n regions. Now let's consider another way of breaking up the input space, which is what you find in neural nets and other models, like factor models and sparse coding, and deep learning in general. So imagine a simple case where I have my two-dimensional input here, and I'm going to learn 3 binary features, and to make it really easy to visualize, imagine those features are just linear classifiers. So what they do is they break the input space into regions. So each of, like the blue one here has this blue hyperplane which breaks the input space in 2, and each of these breaks the input space in a different way. And so now the number of regions they define is the set of all of the intersections of these, the set of corresponding to the set of configurations of those bits. And the number of regions is now exponential in the number of parameters. Wow, so we suddenly have a very different kind of relationship between the number of parameters or the number of examples you need and the number of regions you get. And that allows you to generalize non-locally. Previously, if you wanted to say something about something far away, you needed some example in that region. Now here, I can generalize to a configuration of these attributes that I've never seen before. For example, imagine one of these things tells me that the image is an image of a person that's male versus female, and the other tells me it's young versus old, and the other one tells me the person has glasses or not. And I don't need to see all of the configurations during training in order to generalize to a new configuration of these things, because there's a prior here. The prior is that I can learn about wearing glasses or not without having to see all the configurations of the other factors. So they're not necessarily independent in a statistical sense, but they're independent in the sense that I can learn about each of them without having to see all the configurations of the others. So now let me tell you about maybe the subject which I find the most interesting, which I put as the last bullet in my sort of plan of attack, which is the notion of disentangling. Because I think that this is how we're going to solve the problem of learning the most powerful representations that can really make the learning task, nail the learning task. And this is related to an earlier notion, which is very popular, for example, in computer vision, which is the notion of invariance. So the idea of invariance, which is used, say, in speech or object recognition, makes sense in supervised learning setup. And we say we want to have features that are going to be invariant to the things we don't care. So if I'm going to be doing speech recognition, I want to throw away features that are specific to the speaker. I want to only retain information that's sensitive to the phonemes. So in object recognition, we want to have features that are invariant to the lighting or to the position of the object, things like that. So that's what invariance is about. But if you're doing unsupervised learning, or if you're doing multitask learning, if you don't know what the task is going to be, the most sort of general question you can ask is, well, can I find features that are invariant to some aspects of the data and very sensitive to other aspects? Basically, they extract some factor and they're completely invariant to the variations of the other factors. So in the speech example, if I could have some features that are completely insensitive to the speaker identity, but only carry information about the phoneme, and features that are don't care about what's being pronounced, but only care about the vocal characteristics of the speaker, then I got a kind of disentangling. And that can be learned in principle in a kind of unsupervised way. I don't have to have a task a priori, and maybe one day someone asks me to do speech recognition and I have the right features, and the other day somebody asks me to do speaker identification and I have the right features as well. So that's the idea. And by decomposing the problem like this, the motivation is that we basically nail the problem of the recursive dimensionality, because now we kind of reduce the dimensionality to the features that we care only about for a particular task. And also, the kind of disentangling we have in mind is one where the relationships between the factors of the feature, once you project them in the right space, is very simple, maybe linear or something like that. So, first work on this really is more like an observation study, where researchers at Stanford and in my lab have just looked at existing algorithms, like sparse autoencoders, and observed that the features they learn seem to be displaying a little bit of that kind of disentanglement, that some of the hidden units seem to be specialized on some particular aspect of the input that we know ahead of time, and others could be very insensitive or invariant to other factors like geometric variations in the case of images. And this is nice, but it sort of arises and we don't understand why. We have these algorithms and they learn representations. So a lot of my current thinking is, why is this happening? And if we understand the principle, can we build better algorithms that do that, much better? Another thought is that, if you have zero prior knowledge, then there's maybe no sort of no unique way of doing this kind of disentangling. And if we can give extra prior knowledge to the machine, like some kind of hints, that might help. So the basic hint is that, well, we have representation and we have these factors. This is already a hypothesis, which is the hypothesis I've been talking about earlier, that we have a distributed representation, we have these underlying factors. The depth that I've been talking about is another hypothesis that these factors can be organized or constructed through multiple levels of abstraction or multiple levels of computation. But there are other priors, like the semi-supervised prior that says that if you're interested in a supervised learning problem with input X and target Y, then Y is one of the factors that explains X. It doesn't have to be the case. Like, I could generate my input in a totally random way that has nothing to do with my classification task. And then the semi-supervised learning would fail. But if this prior is verified, which actually makes sense from a causal learning perspective, because we think of Y as one of the factors that explain X, that cause X, then it's very powerful. It allows us to exploit unlabeled data in order to learn representations that can then be useful for supervised learning with very few examples. The multitask prior is similar. It says that if we're going to have a different set of tasks, well, we just share some subset of a larger pool of factors. The manifold hypothesis I already mentioned. It says that probability mass is concentrated. The clustering hypothesis is another interesting one, which is very central, I think, in AI, when, at least even in classical AI, I think maybe people put too much emphasis on it. And it's about the notion of category, of discrete concepts that explain part of what's going on in the world. And from my geometric perspective, what it means is that the data concentrate on these manifolds, but you have a bunch of different manifolds, and these different manifolds are well separated and correspond to natural classes. And actually, the picture is more subtle because it might be that these separation happens under some dimensions when you project in some directions, and so it's not such a simple, clean picture. Then there's another prior which has been around for a long time in the neural nets literature. It's the idea of temporal and spatial coherence. The idea that high-level concepts, the kind of high-level factors we want to discover, tend to remain as they are and keep their value, even though the input changes over time or over space. If I move my eyes, I have roughly the same set of people in front of me. Lots of things remain the same. Another example of such a prior that's very broad is a sparsity prior. And once you think about it in terms of these underlying generative factors, it really says that for any particular input, there's only a small subset of the explanatory factors that are involved. So most of the other factors are irrelevant. It's also a prior. It doesn't have to be true in general. So, it's good to state it and use it if you think it's appropriate. And then there's another prior which I quickly mentioned just a few slides ago, which is that in the right representation, the factors are related to each other in a very simple way, maybe linearly. So, so again, it doesn't have to be true, but these kinds of priors are what I believe we need to help us disentangle the true explanatory factors. Now, I want to tell you a little bit about some work we did last year at ICML. We tried to understand this notion of abstractions and disentangling from the point of view of manifolds. And let me tell you about the experiment. So the experiment, we've trained different deep nets that are with unsupervised learning, either stacks of contractive autoencoders or denoising autoencoders or RBMs, and we observe the same kind of thing. And what we are doing is we're going to take each example, and with these methods we can map them to a new space, and then map them back. But when they're in this new space, we can do things with them, like we can do linear interpolation. So in the input space, like pixel space, if you take the image of a 9 and the image of a 3, and you do linear interpolation, you get these images that are in between the 9 and the 3, but they're just the addition, right? Linear interpolation is addition. So you just get a 9 pasted on top of a 3, it's not very nice, it doesn't look like a natural image. But if you first map the 9 or the 3 in these higher level representations that have been learned by unsupervised learning, and then you do the linear interpolation, and then you take the linear interpolated representation and you project it back in input space, then you get these images. And the funny thing is, they all look all the way along the linear interpolation, they all look like natural images. So what does it mean? It means a number of things. It means that the manifolds on which the data was living, like the 3s and the 9s, they are highly curved in input space. So when you linearly interpolate between 2 points, the thing in the middle doesn't look like a plausible configuration. However, when you project it higher up in the hidden layer space, and then you do linear interpolation, the things in between have a high probability. And what that means is that the manifolds have been flattened. And that's exactly the kind of thing we want. Another perspective on this is that in the input space, the original manifolds are very, very thin. They don't occupy a lot of volume. And when you project higher up, most of the volume is occupied by plausible configurations. So now, even if you interpolate between different classes, you end up with something that's, that tends to be plausible. So my most recent work, which is posted in our archive just 1 week ago, is about extracting structure from data by gradual disentangling and unfolding of these manifolds. And the idea is that we're going to learn a series of representations with encoders and decoders. So F1 is a function, G1 is trying to invert it, and so on. And we start with the distribution. The data has a complicated manifold distribution. We call it Q of X. And when we map it to a higher level representation, we essentially map the original distribution Q of X to a new distribution Q of H1 through a conditional distribution Q of H1 given X, which you can think just as a function. And the way we're going to think of generating the data is we're going to have some kind of model of how to generate the data at that level. And we're going to call that P of H1. And we also have a way to map the data back in input space with P of X given H1. And of course, now you notice that there are 2 ways you can generate X and H together. One is to start from the data and map it up, or you start from your dream in this high-level space of abstraction, and then you map it back. Okay, so you have these 2 ways of generating the data. And one of them we labeled with the letter Q, and the other with the letter P. Well, it turns out that there's a very nice learning principle that emerges if you give yourself as a training criterion the minimization of the KL divergence between these 2 joint distributions. And unlike the original likelihood, which is intractable, this is very tractable. And there's already some work that uses this kind of criterion that started with Dirk Kingman, Max Welling in Amsterdam, and the DeepMind people as well, that explores these kinds of criteria. But what I'm proposing is to use these kind of criteria to train deep architectures where at each level we're trying to disentangle a little bit more, so that at the end of the day, the manifold is flattened and your model P of H is now a better way to capture how the data looks like. So in the original space here, if I had a big Gaussian to represent that, it would be a very bad model when I generate. But higher up, when I generate from this very, very thin, flat Gaussian, what it generates is going to look very, very similarly to the data when it's projected through my encoder. And then I can project it back through all the decoders into something that looks like the data. And we tried things like this, and it seems to work. In addition, it turns out that these ideas allow us, I believe, we haven't tried that yet, to get rid of backdrop. So backdrop has been sort of the central engine of a lot of what we do in deep learning. But it has a fundamental limitation, which is that it relies on infinitesimal changes in order to figure out how to learn, how to change what parameters do, how to change what neurons do. And the reason this is a problem is that as we try to learn more abstract things, we're trying to learn more nonlinear things. For example, if you look at a deep net, what it is a composition of nonlinearity. So if you compose this curve with this one and so on, you get something that's sharper and sharper, and eventually it looks like discrete. And we know that we can't optimize discrete things with gradient descent with backprop. And even before we get into discrete, we see that optimization becomes hard. We see that it's really hard to train very deep nets. And we know of this phenomenon. I've been studying this phenomenon since the early 90s with recurrent nets. And it gives rise to gradient vanishing or gradient exploding. Because what happens is with here, the gradient is either very close to zero when you're in the flat regions, which is going to be the majority of the case, or you're in the regions where the derivative is very, very large, and then when you do a gradient step, you go to hell. So, so these are very bad things from an engineering point of view, but they're also bad from, backprop is also considered not biologically plausible. We'd like to have an algorithm that, you know, every neuron in real time computes the same kind of thing and updates in a similar way. And if we could find such a recipe, I mean, it would be amazing. And it turns out that this principle, I'm claiming it's a conjecture, gives rise to very simple learning, two learning principles that neurons could follow in order to minimize the scale divergence I was talking about before. And basically, it's something like this. Part of it is something not unusual. It says that neurons are trying to predict their future values. So biologists, you know, assume that's already the case, that there's this kind of change. In other words, the synapses that are involved in producing an activation at time t are going to be changed so that the activation after the change would look more like what the value of the neuron would be t plus delta a little bit later. But the new piece that I'm proposing is needed to get this, to actually essentially optimize the criterion I was talking about earlier, is that each neuron is also trying to match its past. So in other words, the synapses that are involved in producing an activation at time t plus delta, they should change so that the activation at t plus delta would have been different with that change, and closer to what the activation was at t, a little bit earlier. So the future values are changed so that they look more like the past values, and the past values are changed so that they look more like the future values. And this new thing of predicting the past basically is the reconstruction criterion that comes up in the KL thing. Through every loop, we should have a good autoencoder. Every loop through the system is trying to reconstruct the past value. That's what reconstruction is, right? The information goes through the network somewhere and comes back later, and when it comes back, it's trying to reconstruct what the old value was. That's what this is embodying. The nice thing with this principle is that it doesn't depend on the form of activation function. It doesn't require symmetric weights. It doesn't require differentiability. It's not tied to using rates or spikes. It could potentially be used on spiking stochastic neurons. All right, so I think I've used a good deal of my time. I would like to...
I'm curious, at risk of taking slightly...
Yeah, go ahead. Yes.
I'm curious for a little more elaboration on your intuition as to why this will do assignment of credit over
right. Okay, I can answer that. So if we look at this picture, what's going to happen is that, so the G's are the reconstruction paths here. They're going to play the role of backprop. So you can think of it like, instead of doing backprop, we're going to have synapses that learn to do something like backprop. And there's a mathematical result, which we showed last year, which is a key element of this, which is that the difference between the reconstruction and the original value is a vector, and that vector points in the direction of higher probability. So it's an estimator of d log p d whatever h here, whatever the thing we're trying to reconstruct. So in other words, a node encoder, the way it's trained, is trying to take its input and map it through the reconstruction into something more probable. So if you now take that more probable thing as a target, that will tell the things below how to change so as to match that target.
Does that relate to the natural gradients of that?
No. And now this is kind of an unsupervised learning principle, but if you stick other modalities or labels on top, then what's going to happen is the information is going to flow up, and then we're going to have these other modalities or labels that are observed at the same time as the input. And then the reconstruction for the top level is going to be, how do I change, it's going to say, how do I change my output so as to be more compatible with the other things I observe? That essentially plays the role of the error propagation in backdrop. In fact, we can formally show that it is an estimator of the gradient of the joint probability or the conditional probability of the labels given the input. And so I would need a whole other talk to explain this in detail, and I have a paper which you can look at. But I hope this helps you to see how this can possibly happen. Yes.
When you say shift to more probable, do you mean basically you're taking the data but moving it towards the center of the galaxy that the full array of the data represents?
Well, there's no Gaussian. So let me imagine that the data is like in this on this curve, right? So any point is sitting on, any example is sitting on this curve, and the way we actually train these autoencoders, especially the denoising autoencoder, is going to help answer your question. The way we train it is we take an example and we add a little bit of noise. So now we're going to be off of this manifold slightly. And now the input of the encoder is going to be this corrupted thing. And the target is going to be the clean thing. That's why it's called denoising autoencoder. That's how we train it. So it's trained to go from a slightly less probable thing to a more probable thing. And that's it. It learns how to move from improbable things to more probable things. And when you train autoencoders, even the non-denoising ones, you see this property that they go towards more prototypical things. But when they're trained very well, they just go to a nearby mode of the distribution. So if you actually iterate, go encode, decode, encode, decode, you just essentially doing gradient ascent on the probability towards more probable configurations. Does that help answering your question?
Yes.
Yeah.
Do novel inputs become new prior?
Novel inputs become new prior.
Yeah, so for example, you get an
You mean,
input that it's not around there, so it's not related
right.
to your graph. Does
Yes.
it become a new prior? So for example, it becomes a new line on the original graph.
So if you're learning with the new inputs, then it's hopefully going to adapt to try to explain that. So there are two possibilities. Either the new input is explained because when you move up, it sort of fits well with the model on top, and you could have actually generated it, and it really extends the probability over to that thing, then not much learning needs to happen. Or you need to change something in the system in order to put probability mass on that new example. So this learning criterion is basically, it's an extension of the maximum likelihood criterion. It says try to put more probability mass on the things you see. So it's going to try to do what you're saying.
It's always going to try to fit to that though, right? So I mean, if it's something completely outside of this...
Well, it may need to invent a new, it has the freedom to use new dimensions if it needs. So the number of, unlike in PCA, for example, where you fix a number of dimensions, here you can imagine you have a huge pool of possible dimensions, and it has learned that some dimensions are noise, basically the things that are outside the manifold, and some dimensions are signal, which gives you the coordinates on the manifold. But if something completely new comes up, it's probably going to need to use some of the high-level dimensions for explaining that. So maybe it creates a new category or a new axis of variation. Yes?
Yeah, can you just go to the other slide with the two principles?
Yes.
Yeah, so it's just not obvious to me why you can't those two principles in combination would not just be doing smoothing.
Right.
But maybe they are doing smoothing.
They are doing something like slowness prior, right? That things, that concepts that will be detected want to stay the same over time. So it's kind of funny that the slowness prior comes for free. Now, it's a force that, you can think of the force that's applied on these things, but you have all of the forces acting together, which mean that they can't just learn a constant function because you also have synapses going into the things that are clamped, the observations, and they want to predict that. And because this reconstruction principle means that every loop is a good autoencoder, that means that the synapse is going into the visible things, the pixels or whatever, the low-level measurements, the clamp things, will be matched by other connections going from the input towards this neuron. At every level, the system will try to be a good autoencoder. Every area is going to try to predict the other areas that it's connected to both ways. And so you couldn't do a good job of that if you just map everything to a constant. So you're trying to do something more subtle, which is you're trying to map to something that is as constant as it can, but at the same time preserves all of the information about the input. Yes?
So I have a question concerning non-local generalization. So, for example, in this image you have some very complex curve.
Yeah.
But will the network be able to recognize objects which are will it extrapolate this curve from outside? For example, if you feed your network with an image which is rotated in some range of angles, and you give it then for recognition an image which is rotated for an angle which was not.
Yes, it will extrapolate to these new angles. Because what you have to keep in mind with these manifolds is that actually the data isn't completely filling those manifolds because it's not a 1D manifold, it's a 1000D manifold. And so what it's also doing is extrapolating and interpolating within the manifold to fill in the possible values in between. It's saying, okay, I'm going to, there was this picture I kind of skipped, where we think of the data as giving us some points on the manifold, and really the learning is about guessing, going from this picture to this picture.
Yeah. So it will not recognize rotated image
Well, if it has seen rotations of anything, and it has sort of learned this factor that is rotation that can be disentangled from the other things, it will very easily generalize to other rotations of other objects.
But will it generalize to rotation angles which were not present?
Yes. So this has already been shown with some experiments where we train, not only you will recognize angles you haven't seen, but you can even recognize rotation of objects you have never seen before.
Okay, so and how far does this capability of generalization go?
I think we have still a lot of progress to show, but I think in terms of applications, we already see the impact of this. But there's a lot more research to be done.
I have a specific question concerning examples which were given by Tannenbaum on NIPS 2010 with
the character alphabets that he generated?
Yes.
Yeah.
So, have you any comments on how deep learning techniques can deal with such images?
Yeah, I think we haven't tried to solve this problem. But it's a very interesting problem, and I believe that this idea of learning multiple levels of representations and trying to factor out the explanations will allow to deal with that kind of data set as well.
Okay, and
Now we haven't tried.
the last question concerns the paper titled Intriguing Properties of Neural Networks.
Right, right.
So, as I understand, this paper shows that this interpolation is not as smooth as it's shown on your image.
Right, and the reason is very simple to understand, I think. Well, there are two reasons, as far as I mean, this is, of course, my claims. One of them is that the manifold of images is very, very twisted. So if you get some twists wrong, then as you can move a little bit and be close to a totally different manifold. So, you know, if you imagine your manifold is highly twisted and you don't model it perfectly well, then you can make a small move and get a totally different nearby manifold twist. That's one thing. The other thing is, this experiment was done with purely supervised learning. And purely supervised learning is not even trying to model the manifold. It's only trying to find features that can separate between classes. It doesn't learn features that separate between a class and all the other possible pixel configurations, which is what unsupervised learning is about. And so it can easily go into a pixel configuration that is totally crazy, that is a non-natural image, maybe in a subtle way, and think that it's a tree or a car or whatever.
So the noise and autoencoders will not be subjected to this kind of problem?
So I made the conjecture that unsupervised learning of representations will be much less sensitive to this issue.
Okay, thank you very much.
I guess, yeah, we've got to wrap up soon, but we can have one more question from Paul.
Go ahead.
Back up to the top level on deep learning. So we've seen many different methods that have different kinds of units, different learning algorithms, or
Yes.
combinations of them. Are things well enough understood at this point to understand if there are particular properties of the units and or the learning algorithm required to make it work?
Well, every researcher has a different answer to that one.
So what is your answer?
Well, I just wrote a paper 1 week ago that has all the answers. But for 6 months I have other.
And I've seen different answers. I mean, whether it's learning in stages, whether it's tying in parameters, whether it's doing unsupervised.
Well, so let me say that unsupervised learning is a key element of the story. I don't think that we can get AI with just supervised learning.
So, for example, if we did, if we just use multilayer Bayesian network with gradient descent,
Yeah.
does that likely work, or is there any criteria by which we know whether it will work or not?
I think you need to do more research on it. But the criterion I use is experiments. And also, maybe even more important is some kind of mental picture I build of trying to get a coherent view of the goals that I'm trying to achieve. But of course, a different person may have a different opinion.
All right, well, thanks. Yeah, thanks, Yoshua, for an excellent talk. That was actually more than I expected. I thought it would be an interesting talk, but we actually got some new results. The idea of being able to replace backprop in this kind of network with a more local learning rule is something that, of course, everyone's been looking for a long time. So to the extent this really works, it's very exciting.
We don't know yet.
Yeah, I've downloaded the paper from archive. I'll be reading it over the next couple of days. I mean, that's quite interesting. So, yeah, one brief logistic announcement before we're released to the coffee break. So on Sunday evening, tomorrow evening, there will be an optional group dinner, which will be at a restaurant near in the old town of Quebec. So the cost is not part of the registration, so it's sort of just a chance to get together and have dinner with others from the conference. But if you want to join us for dinner Sunday night, there's a sign-up sheet on the table outside. Now, if you neglect to sign up on the sheet, you can come anyway, but we want to get a rough estimate of how many people will be there in order to tell the restaurant. So if you're pretty sure you're going to come along, put your name out there. Again, there's no obligation, so if you put your name down and find something much more exciting to do, that's all right as well. That will be Sunday after the poster session. And I think that's all for practicalities. We can go out and have some coffee and muffins and then